Hi all, we're taking a look at the Achieve Section 2.6 homework assignment. This one's unfortunately a little quick just because of the limitations of the platform not allowing you to show out all of the work in these squeeze theorem proofs. So the first few problems, you'll notice, hey, look at the answers, 0, 0, 0, 0, 0. So I think that at least the first 5 problems you can get through super quick by just putting in 0 because your answers will be the same as mine. But please make sure you understand the concepts behind the squeeze theorem in each of these problems. If I ask you to prove that as the limit as x approaches 0 of x squared times the cosine of 2 over x, prove to me that that is equal to 0. The logic that you would use is you'd say, well, I can't just plug a 0 into the expression because it would be the cosine of an undefined angle. But what we know is that the limit could care less if it's undefined at the value. It only cares about what happens as we near that value. So here's what I do is I show that the cosine of 2 over x, whenever it does exist, and it will exist for all x values other than 0. So for any other value other than 0 itself, we know the cosine of 2 over x is between -1 and 1. Therefore, the smallest this original function could ever be is when we multiply x squared by -1. And so we say our original function is greater than or equal to x squared times -1, but it's less than or equal to x squared times +1. Again, since the cosine is greater than or equal to -1, and since the cosine is less than or equal to 1. Now I show that the small and large function have the same limiting value. And I can say, well, it doesn't matter if the cosine is -1 or +1. The limit as x approaches 0 of x squared times -1 is the same as the limit as x approaches 0 of x squared times +1, which are both 0. Therefore, we can say the limit of our original problem is 0. And you can see that's what I had here on my problem on Achieved. Now, for the next question, very similar. And in fact, all of these first questions are similar. So I think I'm just going to maximize this screen right here. Yeah. So the second question, again, was a squeeze theorem proof. It asked me to show that the limit as x approaches 8 of the group x minus 8 times the sine of 8 pi over 5 times x minus 8. Well, the problem with trying to plug an 8 into this expression, no problem at all with the first, x minus 8 exists at 8, but this sine function would not exist when it has a denominator of 0. And if you try to plug an 8, you get a factor of 0 in the denominator of that sine fraction argument. So you say, okay, can't just evaluate 8. So instead, I say, well, wherever the sine does exist, it's greater than or equal to -1 and less than 1. Therefore, my original problem is greater than x minus 8 times -1. So here's my original problem. I know it's greater than or equal to if we replace sine with a -1, and it's less than or equal to if I replace sine with a +1 times the remaining portion, x minus 8. So now I show that the limit as x approaches 8 of the smallest our function could be and of the largest our function could be have the same limiting value. That's what I do. The limit as x approaches 8 of x minus 8 times -1 or times an understood +1 is just 0 times 1 or 0 times -1, which is 0. Therefore, the limit as x approaches 8 of our original function is also 0. Now, this whole thing would be required if you were doing a squeeze theorem proof. Sadly, Achieve has no way of having you put all of these steps in. They're just asking for the final answer, which is almost always 0 when we're looking at trig limits. Our next one here, we have the limit as t approaches 0 of the exponential function 8 to the t minus 1. That's being multiplied by the cosine of 3 over t. Well, I can plug a t equals 0 into this. 8 to the 0 power is 1. 1 minus 1 is going to give me a 0. The problem is the cosine of 3 over 0 does not exist. And again, I know, well, the limit doesn't care if it doesn't exist at 0. It cares about what happens as we near 0. So I can say, well, for any other value of t other than 0, this cosine function exists. When it exists, it's always between -1 and +1. That instantly sets up a small function and a large function. Our small function is going to be 8 to the t minus 1 times a -1. Our large function is going to be 8t minus 1 times the largest the cosine can be, a +1. Now, as soon as you get your original function in between a small and a large function, now you just say, well, show that this small and large function have the same limiting value. I do that. The limit as t approaches 0 of 8 to the t minus 1 times -1 is equal to the limit as t approaches 0 of 8 to the t minus 1 times +1. And in either scenario, if you let t equal 0, 8 to the 0 minus 1, that's 1 minus 1, we get a factor of 0 times a number that's either negative or +1. Doesn't matter if it's negative or +1. Any number times 0 is 0. Therefore, we say the limit of our original expression is also 0. For number 4 here, I had the limit as t approaches 9 of t squared minus 81 times the cosine of 3 over t minus 9. And just like in the earlier problems, it's not the quadratic portion of this one that's the problem. I can plug a 9 into that, no problem. But I can't plug a 9 into the denominator of that fraction that's the angle inside the cosine function. It makes the cosine of an undefined angle. But I can say, well, the only place that this is going to be undefined is at 9. I'm trying to show what the limit as t approaches 9 is. So I can say, well, wherever the cosine function is defined, which it's defined for all values other than 9, it's going to be a number between -1 and +1. That, again, allows us to set up a small function by replacing cosine with -1, and it allows us to set up a large function where we replace cosine with a +1. Now, the only thing we have to do, this function is guaranteed to be in between these two functions. So if I can show that the small and large function have the same limiting value, our function that we're trying to show has to have that limiting value. It's going to be true again. T squared minus 81 times -1. The limit as t approaches 9 of that is going to equal the limit as t approaches 9 of t squared minus 81 times 1. If I plug the 9 into this quadratic portion, it's 81 minus 81. So you have 0 times either -1 or 1, which in either case is 0. Therefore, the limit as t approaches 9 of our original expression is also 0. Now, I think the last one of these squeeze theorem problems, number 5, we had the limit as theta approaches 17 pi over 2 of the cosine of theta times the cosine of the tangent of theta. So now, I know that the cosine at any of any increment of pi over 2, or I should say any odd increment of pi over 2, it's either going to be straight up on my unit circle or straight down on my unit circle. That's 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, all the way up to 17 pi over 2. The cosine at any of those values is 0. But that one's defined. I could plug it in there. What about here? I can't plug it in. Why? Well, because again, it's going to be the tangent of 9 times 17 pi over 2. That's still an odd multiple of pi over 2, which is going to be either straight up or straight down on your unit circle. The important part of that is that the tangent is sine over cosine. The denominator of this tangent function is going to be 0. So you say, well, I can't have that. It makes the tangent undefined. The tangent of any odd multiple of pi over 2 is undefined. That's what has to be handled in this problem. So I have the cosine of an undefined angle. I can say, well, the only angle where it's undefined is at 17 pi over 2 itself. It's not going to be undefined for any other angle other than that one. So I can say, well, wherever the cosine of the tangent is defined, I know that the cosine of any angle is between -1 and 1, just due to the range of the cosine function. That allows me to set up my small function by saying, well, I'll replace the cosine of the tangent of 9 theta with a -1 and multiply it by the cosine to form my small function. I'll replace the cosine of the tangent of 9 theta with a +1 to multiply by cosine to create my large function. Now I can say I know that the function that we're trying to find is somewhere in between these two values. Okay, now take the limit as theta approaches 17 pi over 2 of the small and large function. And when you do that, if you plug a 17 pi over 2 in there, that cosine of 17 pi over 2 becomes 0. 0 times -1 or 1 is 0. Therefore, we can say the limit as theta approaches pi over 2 of the cosine times the cosine of the tangent of theta is also 0. Since it was guaranteed to be in between that small and large function, those two had the same limiting value. Thus, the limiting value of what we were looking for also had to be 0. Now, I've looked through the first 5 problems that all dealt with the squeeze theorem. After that, they start getting to your other trig identities, which remember, the 2 formulas that you'll need to know for this section are the limit as h approaches 0, the sine of h over h is 1, and the limit as h approaches 0 of 1 minus cosine h over h is 0. The last several problems use those 2 formulas, most of them the sine formula. When I'm looking at number 6, now, sadly, again, in these, you can make all these problems so easy. I would rather you show your work, but I'll never know if you show your work. When I'm looking at this one, I'm thinking, the answer is 2 over 11. Now, the next one's a little tricky because you might think, well, hey, is your answer 4 in the next one? It's not going to be 4 because that's a sine squared up there. But in this one, as long as it's all to the first, I can just look at that one and say, well, my answer is going to be 2 over 11. But now, let's show where the answer comes from. Because you don't want to just do it the wimpy way. You want to know how the problem is shown out. Yes. Okay, so let's do that. I break the tangent of 2x. I know that the tangent is the ratio of sine over cosine. So the tangent of 2x becomes sine of 2x over cosine 2x. I left my 11x as a factor in the denominator, still have the limit as x approaches 0. Now, I'm remembering back to what we had in our notes for this section, and I'll pull that here real quick. This is what I was talking about. The notes that we had in this section, I need to get that the sine of an angle over that angle as that angle is approaching 0 to call that 1. Or the reciprocal of that relationship. So that's my goal in all of these problems. So as soon as I see a sine of 2x up there, I know I want a denominator of 2x. But now, hopefully you're thinking, well, you can't just put a 2x in that denominator. No. But if I multiply a denominator in a problem by 2x, then I need to make up for it by multiplying a numerator by 2x. So what I did, and it's hard to see in the order that I did this work, is I went ahead and created a fraction with a sine of 2x in the numerator, a cosine 2x in the denominator, and a third fraction with an 11x in the denominator. So I put a separate fraction for all 3 terms that you see here. Now, the first fraction I knew I wanted to make equal 1. I had to multiply by 2x in the denominator. So I took the third fraction, which I had a blank numerator, and said, well, if I multiply denominator by 2x, I need to multiply numerator by 2x. I went ahead and did that. Then in this second term, I didn't need anything there. Why don't I need anything? Because as x approaches 0, this becomes the cosine of 2 times 0, which is the cosine of 0. The cosine of 0 is defined to be 1, so I'll just say, well, then that second fraction is 1 when I take the limit. So by definition, the sine of an angle over an angle as that angle approaches 0 is 1. My second fraction by definition is 1. My third fraction, the x's would cancel, and you'd just be left with 2 over 11. So we have 1 times 2 over 11, final answer. And again, I know it's so tempting just to look at it from the very beginning and say, John, I already know my answer is 2 over 11. Do I really have to show my work? And I would say, well, you don't have to, but I would like you to understand where it's coming from. Okay, number 7. We have the limit as t approaches 0, the sine squared of 4t over t. So I went ahead and said, well, this limit is going to be, since it's sine squared 4t, that means the sine of 4t times the sine of 4t. You'll notice I took that divided by t, and I went ahead and created a third fraction with a t in its denominator. Why did I move it over there? Well, because both of these denominators, it's already concluded what it has to be. In order for this fraction to become 1, as I take the limit as t approaches 0, whatever that angle is has to be in the denominator. So I multiplied by 4t in this denominator, I multiplied by 4t in this denominator. I can do that if I also multiply by 4t twice in the numerator. But I wanted a separate fraction over here that I'm multiplying, so I multiplied by 4t twice in that numerator. This t came over and became the denominator of this third fraction. Now notice what happens though. You can say, well, these two, that's the exact same thing. I could write it as the group squared. And I know that when I take the limit, these fractions just become 1 anyway. So this is going to become 1 times 1, or over here you could think of it as 1 squared. My other one, I have 4t times 4t is 16t to the second divided by t. That's multiplying by 16t to the first. Allow t to go to 0. By definition, these become 1. This is going to become 16 times 0, so we have 1 times 16 times 0. Any number times 0? 0. We get our final answer there. For number 8, we have the limit of, as x approaches 0, of x squared over sine squared of 14x. So similar to the last problem, I said I need to write this sine squared of 14x in my denominator twice as sine of 14x, sine of 14x. I went ahead and put the term of x squared over in the numerator of the third fraction. Now, in order to make these fractions equal to 1, I need whatever the angle is in the other part of the fraction as a factor. So I put a 14x in this numerator, I multiplied a 14x in this numerator. If you multiply the numerator twice by 14x, you have to multiply the denominator twice by 14x. Now, I know that these first two fractions, when I take the limit as x approaches 0, by definition, they become a 1. The third fraction, notice if I multiplied my denominator, 14 times 14 is 196, and then I would have an x squared. That x squared can cancel with a factor of x squared in the numerator, and then that's just going to leave me 1 over 196. So now when I take the limit in this last step, the limit as x approaches 0, the first two expressions, 1 times 1. There is no x remaining in this one, so you just have a 1 over 196. 1 times 1 times 1 over 196 for our final answer of 1 over 196. That's a cool problem. I like that one. The next one here, number 9. You're taking the limit as x approaches 0 of the secant of 5x minus 1 over 4x. So as soon as I looked at this problem, I'm thinking, well, the secant, it's 1 over the cosine of 5x. That automatically puts a fraction inside of your fraction. So my first step in thinking, how is this going to simplify? I'm going to get rid of the fraction in the fraction by getting rid of that secant by multiplying by its reciprocal, the cosine of 5x. And if I do that in the numerator, I must also do it in the denominator. Now, as I try to simplify this, my numerator, secant of 5x, which is the same thing as 1 over cosine 5x, times cosine 5x gives me a 1. I distribute that into the second term to get the minus cosine of 5x. Now, my denominator, 4x times the cosine of 5x. So I know that my cosine formula, and again, let me pull our notes from the section. Our cosine formula is if I have 1 minus the cosine of an angle divided by that same angle in the denominator, and if I take the limit as that angle approaches 0, that's going to be a value of 0 in my problem. Okay, so my goal is to try to get to that. I have 1 minus the cosine of 5x, so I need to put a 5x in that denominator. Now, I can't put a 5x in the denominator if I don't multiply the numerator by 5x. So I did that, and then you see the existing denominator that was already under this, I just slid over to my second denominator. Completely legal maneuver. The only thing I've done from this step to this step is multiply by an understood 1 of 5x over 5x. But I wanted the 5x in the denominator of this one, so I could say, well, now this is automatically going to be in the form of the limit as theta approaches 0 of 1 minus cosine theta over theta, and I know that that expression is equal to 1. Sorry, to 0, not 1, 0. So now it's really irrelevant what the second one's equal to, since the first one's going to be a factor of 0. Technically, in the second one, your x's cancel, and you have 5 over 4 cosine of 5x. If you allow x to approach 0, our first expression becomes a 0. Our second expression would become 5 over 4 times 1, which is 5/4. But again, doesn't matter that you get a real number for the second one, because 0 times any real number is just going to be a value of 0. So number 9, done. Number 10 here. This one's just, I started to say just by definition, the sine of t over t as t approaches 0 would be 1, but we're approaching a different value here. In this one, the only time it would be indeterminate and you have to use the definition is if the angle is approaching 0. That's not the case here. The t is approaching 5 over 4. You just plug it in. And we know 5 over 4 splits quadrant 3. And at that point, our sine is the negative square root of 2 over 2. We're dividing that by 5 pi over 4. So you say, well, if you're dividing by a fraction, you're multiplying by the reciprocal of that fraction. Get negative 2 over 2 times 4 over 5 pi. All I did is I reduced the 4 over 2 down to 2, and I said, well, that's going to be negative 2 on the root of 2 over 5 pi. Final answer, gorgeous answer. And please notice, it's wanting exact notation. It doesn't want you evaluating the root of 2 as a decimal or pi as a decimal. That would be an inferior and marked incorrect answer. The next one is, again, one of our easy questions. I would just want you to look at this and say, John, the answer is 8, because it's going to be 8 over 1 here. Now, where that answer comes from is we go in and say, well, okay, if we have the limit as h approaches 0 of the sine of the angle 8h, we know we need that angle in the denominator. So I multiply the denominator by 8h, which then means I need to multiply numerator by 8h. I do that. I move over the h that was in the original denominator over here. Now this second part's going to reduce down to just times 8. The first part, by definition, as an angle approaches 0, the sine of that angle over that angle approaches 1. And then we have times 8. 1 times 8 is 8. That eliminates the need for that problem. Last part of this, or the last page it took me to do this homework assignment. Number 12, we have, again, this is one of the annoying ones. You can just look at it and say, John, the answer is 1 over 10. It is. Where that comes from, though, if I have the angle going to 0, I need that angle in the denominator. Well, I can easily call it the sine of h over h. If I separate the factor of 10 from that h and just multiply this fraction by 1/10, then you can say, yep, this is equal to the original expression, but now I can clearly see that if I let h go to 0, the sine of h over h all approaches 1. We have 1 times 1/10 for our answer of 1/10. Not a fan of that problem. Number 13 here. Mercy. Again, you could just look at it and say, this one's 2/5, John. It is. The reason we can say it's 2/5 is because I can put the sine of 2 theta in the numerator, the sine of 5 theta in the denominator. If I put the sine of 2 theta in the numerator, the only way that that limit's going to approach 1 is if its angle is in the denominator. So I multiply by 2 theta in the denominator, I have to multiply by 2 theta in the numerator. Here I have the sine of 5 theta. I have to have that angle in the numerator, so I multiply the numerator by 5 theta, make up for it by multiplying the denominator by 5 theta. And then you can say, well, by definition, these first two are just fractions equal to 1 when you take the limit. The last one, the thetas would cancel, and you're just left with 2/5. So when we take the limit as theta approaches 0, we have 1 times 1 times 2/5 for our final answer of 2/5. For 14, It's, again, the limit is not approaching 0, so we can evaluate this one by just plugging it in. I went ahead and showed this here. We have the x over the cosecant of 27x. So whenever I'm trying to plug that in, I can say, well, if x is approaching pi over 4, my numerator is, or it becomes pi over 4 when I take the limit. My denominator is the cosecant of 27 pi over 4. Now, when I thought about that, I just said, well, okay, 4 is going to go into 27 6 times, and it would leave me 3 pi over 4 over. So I'm thinking, okay, I know 6 pi is 3 revolutions of the unit circle, because 2 pi plus 2 pi is 4 pi plus 2 pi is 6 pi. So 27 pi over 4 is 6 pi plus 3 pi over 4. So I just thought, then 27 pi over 4 is coterminal to 3 pi over 4, which means its cosine is the negative square root of 2 over 2, and its sine is the square root of 2 over 2. Well, I have the cosecant. I know that the cosecant is just the reciprocal of the sine, so it'd be 2 over the root of 2, which is just the root of 2. So then you could say, well, all right, the cosecant of 27 pi over 4 is the root of 2, but now we have pi over 4 divided by the root of 2. Well, if you have pi dividing by 4 and it's dividing by the root of 2, then your final answer is pi over 4 on the root of 2. Now you could think of this as, if you wanted to divide by the root of 2, you could multiply by 1 over the root of 2, same thing. And then you could see that, yeah, this is just going to be pi over 4 root of 2. Final answer there. And you can see that Achieve did want that exact notation. For 15, this goes back to be one of the annoying ones, because you could just look at the original problem and say, oh, John, I bet the answer is negative 3 over 2. Yes, yes, it is. Now, the reason that that works is because that sine of negative 3 theta, since that angle is approaching 0, in order for this fraction to approach 1, I need that angle in the denominator. So you'll see I multiplied by in this denominator by negative 3 theta. I can do that if I go to another fraction and multiply the numerator by negative 3 theta. So that's where that came from. Now, I separated the sine of 2 theta in the denominator into a second fraction. Now, I needed a 2 theta in the numerator of this, so I would multiply the numerator by a 2 theta, and that's okay, as long as I multiply a denominator by 2 theta. So this last fraction I frequently call the dummy fraction. It's just taking care of any multiplication of 1. If I multiply a denominator by negative 3 theta here to make this fraction 1, multiply the numerator here. If I multiply this numerator by 2 theta, I multiply this denominator here. That's just to keep our fraction worth what it should throughout the entire problem. Now, just as in several problems earlier, by definition, the sine of an angle over an angle, if that angles are going to 0, these are equal to 1. Your last one, the thetas would cancel, and it's just going to go to negative 3 over 2. Thus, our final answer, negative 3 over 2. For 16 here. This is another one. You could have just looked at it in the first part and said, ooh, John, I bet the answer is going to be 2 over 3. If you think that, you can see absolutely right. Now, here's the reason why that works in this problem. I know that the tangent of 2x is sine of 2x over cosine 2x. Well, I'm dividing that by the tangent of 3x. Well, I know that the tangent of 3x would be sine of 3x over cosine of 3x. Since I'm dividing by it, I just said, well, let's multiply by the reciprocal of tangent, which would give me cosine 3x over the sine of 3x. Now, as I did this, these cosines I'm really not worried about, because the cosine of 0 is 1. These are just going to be factors of 1s. The ones I'm worried about are the sines. So I can say, well, all right, I'll have the sine of 2x. I'll need to divide by 2x. If I divide by 2x that wasn't previously there, I need to multiply a numerator by 2x. That's where that came from. Then you'll see my second fraction, I have the sine of 3x in the denominator, and then I went in and multiplied the numerator by a factor of 3x that wasn't there ahead of or before that. So I had to divide by 3x in my last fraction. You'll see I handled the cosine of 3x over the cosine of 2x right here. At that point, we're ready to take the limit. The first two, by the limit definition, become 1. So I can say, well, the first term is 1, the second term is 1, the cosine of 0 is 1, so that's just 1 over 1. Your last one, your x's would cancel out, and you would have 2/3. Final answer, 2/3 for 17. So in this one, again, it's a little harder, but you could see the answer from the beginning. You say, oh, I bet I just multiply that 10 times 5 over a 1 times 7. I bet my answer is 2 times 5 is 10 over 7, 10 sevenths. Ding, 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 ding. Here's why that works, though. You'd say, okay, I'm going to take that sine of 2x and that sine of 5x and create separate fractions. I don't want the x or the sine of 7x in its denominator. What do I want in this denominator? Always, always the angle. So I need a 2x in this denominator. I need a 5x in this denominator. So now notice I multiplied by 5x, and actually what I did is I said I already had an x, so I just needed another factor of 2. So all I did is multiplied my denominator here by 2, multiply my numerator by 2. And then I needed the whole 5x for the sine of 5x, so I had to multiply by 5x up here. Now, for the sine of 7x in the denominator, for this part of the fraction, I can say, well, I need a numerator of 7x. So I multiplied by the numerator by 7x, have to multiply the denominator by 7x. Now, anytime you have the sine of an angle over an angle, or an angle over the sine of that angle, if that angle is going to 0, these fractions are going to 1 as we take the limit. So I have 1 times 1 times 1. This last one, the x's would cancel, and you'd be left with 10 sevenths. Gorgeous stuff. The last one, it's a bit tricky. Normally, I think anytime I see that 1 minus the cosine in there, I'm thinking that the answer should be 0. This one, not, because we're not taking the limit as h approaches 0. This is actually similar to one of our sine problems where we had number 10. You say, well, if it were just the sine of t over t as t approaches 0, my answer would be 1. But as t approaches 5 over 4, I can just plug that in. Same thing here. We plug in the negative pi over 2. And so you say, well, this is going to be 1 minus the cosine of negative 3 pi over 2 divided by, my denominator is just h, so it's negative pi over 2. So I can say, well, the cosine at negative 3 pi over 2, negative 3 pi over 2 would be right here on your unit circle. You know your cosine's just the x component, so it's a 0. So our numerator is 1 minus 0. My denominator is a negative pi over 2. So I'm saying, well, this is just going to be 1. And if you're dividing by a if you're dividing by a fraction, that's multiplying by the reciprocal of that fraction. So I have 1 times negative 2 over pi, leaving me a final answer of negative 2 over pi. And hopefully you think that problem was a piece of cake. Now, if you do have any questions, let me know. A lot of these problems in this section really should take a lot more time than what it would involve on Achieve, like all of those limit of the squeeze theorem problems at the beginning where we know that the answer is always 0, so it makes those annoyingly easy. But please, please, please make sure you understand the logic and how the proof for the squeeze theorem works. Especially for any of you math majors and stuff, you're going to have problems where you have to understand how to demonstrate the logic of the squeeze theorem in the future. And no, the answer is not always 0 once we get away from strictly sine and cosine and trig limits. Okay, so that'll do it for this section. I'll see you back for 2.7, more fun stuff. And as I was saying, if you have any questions, please let me know.